So we're just going to quickly revisit the time differential. This will be a short lesson, short video, because we're just building on the same concept from before with a few extra additional examples. So hopefully you had some success. You probably had some not so great successes too. You probably had some problems that really threw you for a loop, but the more you practice, the more you'll get more comfortable with these types of related rate problems. So let's take a look at an oil spill. All right, so imagine that this tanker is leaking oil and it's going to float on top of the water, making a roughly circular oil slick. We'll assume it's a perfect circle for our purposes today. And now we have at the time, okay? So remember, that's going to freeze this problem at a specific moment in time, but we are not going to focus on that right now. We are just going to focus on the geometry of it. Okay, and so the question is the area of the oil slick, okay, the rate of the area of the oil slick. So that is in a circular shape, so we know that circles have an area of pi r squared. So we will introduce time and put this problem in motion. So the rate at which the area is changing depending on time will be 2 pi times r, and then times the rate at which the radius is changing depending on the time. Okay, now we are ready to look back and look for some values that we can put in here. So we know that the slick's radius is growing at a rate of 3.5 meters per minute, and so that is going to correspond to the value for dr dt. We are also given that the diameter is 150, which means that the radius must be 75, and so that's going to go in for my r. So now we're freezing this moment in time, and so my rate of which the area is changing with respect to time will be 2 pi times 75 times 3.5. which gives me 525 pi. And now I need the units for this. We are measuring area, so area would be square units, and these are square meters, and the time unit is minutes. So the rate of the area of the oil slick is increasing at a value of 525 pi square meters. And if we want to put that into context, we would actually multiply it by pi. And so that's going to be 1,649.336 square meters per minute. Okay, let's take a look at a little bit more of a complex one. We've got a couple moving things going on here. We've got a train passing by someone who is watching. Okay, so let's put our train tracks on here. And we've got the person, so here are my train tracks. And I have a person 70 meters south. Okay, so that's their distance. And the train is passing by, heading east. It's an eastbound train, so the train is heading towards the east. Okay. It's going to pass directly by the person as they're watching it, and then the train will continue. So the train is going to be continuing to follow along that path. And then the question is, how far or how fast is the train moving away from the observer? So now we want the distance between this train and the observer who is watching it. So that's going to form a nice right triangle for us. So let's call that side maybe the side for the person who's standing still, remember, and then we have the t for the train, and then maybe we'll do x for the distance between them. Okay, all right, and so geometrically, because it's a right triangle, we've got p squared plus t squared equals x squared. So we bring time into the problem, 2p times dp dt plus 2t dt. Careful with your t's because one has to be capital and one has to be lowercase. And then 2x dx dt. And because we have all of these common values of 2, we can reduce the problem by 2 just to make it a little cleaner for us. All right, so we have p dp dt plus t dt dt equals x dx dt. Now we're ready to actually freeze this at a particular moment in time, and the moment in time we are going to freeze it in is 4 seconds after it passes through the intersection. So the time that this has taken has been 4 seconds. So we need to use that time and figure out how far the train has traveled. Well, the train is traveling 60 meters per second. And so in those 4 seconds, the train has traveled 240 meters. So that will be my moment in time. Okay, then I'm going to freeze that. We also know that the person is standing 70 meters south, so we have that value as well. All right, so we've got 70 for the person times dp dt plus the train, 240 times dt dt, and then equals x, and then times dx dt. So a couple things we should be able to figure out here. We should be able to figure out what x is using a little geometry and the Pythagorean theorem. So x has got to be the square root of 70 squared plus 240 squared, which conveniently works out to 250. All right, so we know that our x value is 250. So I can come back over here and put 250 in for x, and dx dt is the speed at which the distance is changing. Okay, now we need our other rates, our related rates. So dp dt is the rate of the person. Now remember, the person is just standing still. They're waiting. So this person is not moving at all. So that's a 0. The speed of the train is 60. And so we end up with basically canceling out that, and we've got 240 times 60. So we're looking at 14,400 equals 250 dx dt. So a simple division. So 57.6 is the speed of the distance between the person and the train, and that distance is measured in meters again, so this would be meters per second. So I hope you are getting more and more comfortable each time. Each time you do one of these problems, it starts to make a little bit more sense, all the moving parts that come together. And so then I look forward to wrestling through some of these with you on Thursday, and then we'll finish up lesson 4.5. All right, see you then.